Hello and welcome to the universe through the Hubble Space Telescope. My name is Fulvia Fiorani. Thank you for joining me as we celebrate Hubble's 30 years of remarkable discoveries. At its launch 30 years ago, no one could have predicted the wonderful images Hubble would bring us. From our own cosmic backyard to the far reaches of the universe, Hubble has shown us a view of the universe beyond our imagination. So this presentation is a journey through our universe as seen through the beautiful images brought to us by the Hubble Space Telescope. As we look at these iconic images, I will briefly cover what we have learned about the universe from these amazing images. Our journey starts with a little bit of information about the telescope itself. Then we will stay close to home and briefly explore our solar system and our own Milky Way galaxy. Hubble has opened a new view into star birth and star death. We will see what we have learned about the stellar life cycle through some of Hubble's most beautiful images. Then we'll look farther away from home, starting first with the nearby galaxies, then galaxies far, far away. And we will end with a very brief look at Hubble's successor. The telescope is named after the American astronomer Edwin Hubble. It was built by NASA with contributions from the European Space Agency and is operated by the Space Telescope Science Institute. It was launched on April 24, 1990, from the Space Shuttle Discovery and was specifically designed to be launched and serviced by Space Shuttle missions. It is in low Earth orbit above the Earth's atmosphere at an altitude of approximately 350 miles, with a speed of 17,000 miles per hour, and at that speed it completes one orbit every 97 minutes. The diameter of the primary mirror is about 8 feet, with a collection area of 48 square feet. And this allows Hubble to collect 230,000 times more light than the human eye. And that's all a telescope really does. It collects more light. Its length is about the size of a school bus. All of Hubble's functions and instruments are powered by sunlight through solar arrays that convert sunlight directly into electrical energy. Hubble was successfully repaired and serviced on 5 servicing missions. Since the Space Shuttle program has ended, there will be no more servicing missions. Hubble's original mission was to last 15 years, but it is still going strong 30 years later. And at the end of its original mission, it was supposed to have been brought back to Earth by the Space Shuttle. But since that is no longer possible, it will simply deorbit into the ocean sometime around the mid-2030s, depending on how long it continues to function. Okay, let's start our cosmic journey with a look at our home in the universe. We first start with our solar system. Now, Hubble cannot observe the Sun or its closest planets, Mercury and Venus, because its instruments are very sensitive to light and they would be damaged by the sunlight. And although Hubble is not designed to look at objects within our solar system, it has nevertheless observed the outer planets and provided us with unprecedented views of these bodies. One of Hubble's advantages is its ability to take high-quality images of short-notice events in our solar system, such as comets and small body impacts, as we'll see in a few slides. Next, we'll take a look at our own Milky Way galaxy. We'll see some star fields at the heart of the galaxy, some beautiful star clusters, and we will end with a look at the center of the Milky Way itself. The first planet we encounter as we go out into space is Mars. Hubble's main contribution to the study of Mars is helping to identify surface features and monitor its weather patterns. This is a view of Mars during its closest approach to Earth in nearly 60,000 years. We can clearly see the southern ice cap, and here we see Olympus Mons, the largest volcano in our solar system. It's the size of Arizona and 3 times as high as Mount Everest. In this view, we see both both of the polar ice caps, and bright frosty clouds revealing that Mars is a dynamic seasonal planet. These images were taken in early December 2007. Each image shows a 90-degree rotation from the next image, and so it gives us a full globe look at Mars. One of the reasons astronomers are interested in studying the changeable surface and weather conditions on Mars is to help plan for the rover missions on the planet's surface. In 1994, Hubble followed Comet Shoemaker-Levy 9 as it crashed into Jupiter. This was the first direct observation of an extraterrestrial collision. The importance of this event is that it sort of woke up the astronomical community to the reality that this could happen to us. Here we see a beautiful image of the comet ripped into pieces by Jupiter's tidal forces and hurtling its way toward the planet. These are some of the giant impact sites. The energy of impact ranges from 1 million to 100 million World War II atomic bombs. The largest impact is approximately the size of Earth. This is a beautiful image of Jupiter revealing the colorful bands of clouds swirling in its atmosphere and Jupiter's trademark, the Great Red Spot. The colorful bands that we see, which flow in opposite directions at various latitudes, result from different atmospheric pressures. And this, of course, is Jupiter's Great Red Spot. It is a giant storm in Jupiter's atmosphere that has persisted for many centuries. It is the largest storm in the solar system, and you can fit 2 Earths into the storm. This is a beautiful montage of Jupiter's Great Red Spot, showing that it is an active storm which changes in time. Next is Saturn with its magnificent rings. This is a great look at Saturn's beautiful ring system over a 4-year period. Now, because of Saturn's axial tilt, we see a different orientation of the rings as Saturn travels on its 29-year journey around the Sun. And this is Hubble's latest view of Saturn. It is simply spectacular. It captures Saturn's ring in superb detail, allowing us to see numerous ringlets and fainter rings. Now, the age and formation of Saturn's rings is still debated, and there is still no consensus among planetary scientists today. Continuing our outward journey, we come to Uranus and Neptune. This series of images shows the ring system of Uranus at different angles as viewed from Earth. Now, the rings were first inferred in 1977 and first seen by Voyager 2 during its flyby in 1986. But Hubble has provided the first images of the ring system as viewed from Earth. This is a beautiful portrait of Neptune in its natural color, along with 4 of its moons. Now, in these images, it reveals a very dynamic atmosphere and the presence of a dark spot or a vortex. The image at right shows that Neptune storms are best seen at the blue wavelengths of light. And only Hubble has the high resolution required for identifying such weather features on distant Neptune. So now we move away from our solar system and go out into our own Milky Way galaxy. As seen with the naked eye, the Milky Way appears as a cloud or a band of starlight that stretches across the sky. We will see that the heart of our galaxy holds a rich field of stars, star clusters, and nebulae. So let's see what Hubble can show us as we look into the heart of our galaxy. We start with the sparkling jewel box of stars. This image clearly shows us that stars come in a variety of colors and brightness. So what does this tell us about the stars? Well, a star's color reveals its surface temperature. Knowing a star's temperature and its luminosity, or its radiation power, tells us a lot about a star. It allows astronomers to calculate a star's mass, which is the most important characteristics, its age, and its size. Most blue stars are very young and hot, up to 10 times hotter than our Sun. They consume their fuel very quickly and therefore live short lives. The red stars come in two types, red dwarfs and red giants. The small red dwarfs have a temperature about half of our Sun, so they consume their fuel very slowly and therefore live much longer lives. The red giants are stars at the end of their lives. Some of them will eventually explode into supernova, and some will quietly die as a white dwarf. Our Sun is a yellow star. In about 5 billion years, it will become a red giant, then fade away quietly as a planetary nebula and a white dwarf. By studying stars at the heart of the Milky Way, we can learn about the evolution of our galaxy. Stellar clusters are groups of stars that were all born about the same time, but they differ in size, mass, and temperature. So they are at different stages of their life cycle, giving astronomers and physicists an opportunity to study stellar evolution. This particular cluster, called Trumpler 14, contains some of the youngest and brightest stars in the Milky Way. The cluster is only 500,000 years old. It is one of the highest concentrations of massive luminous stars in the Milky Way. These stars will explode into supernovae in just a few million years. These stars are on the other end of the spectrum. This is a cluster of ancient white dwarfs. In other words, this is a cluster of dead stars. They're about 12 to 13 billion years old. And this agrees with the current measurements of the age of the universe of 13.8 billion years. This is a beautiful cluster dubbed fireworks because the young bright collection of stars looks like an aerial burst. Beside their beauties, what information can we get from these clusters? Well, most of the stars in a cluster are born at the same time, but they differ in mass, size, temperature, and color. Now, since a cluster contains stars that were all born at the same time, but with different masses, when we observe them, they will all be at different stages of their lives. So studying stellar clusters gives us an opportunity for detailed analysis of stellar life cycles. Now let's see what Hubble sees when it peers into the center of our galaxy. First, let's see what we can see with the naked eye. To find the center of the galaxy, we first find the teapot asterism in Sagittarius. Above the spout of the teapot is the galactic center. But we can't see anything with the naked eye because of the large amount of gas and dust surrounding the center. So let's see what Hubble can show us. Here is what Hubble sees. But even Hubble needs some help because this doesn't really give us a good picture. So we're going to get a little help from two other great space observatories. The first one is from the Spitzer Space Telescope, capturing the low-energy infrared wavelengths of light. This other image is from the Chandra X-ray Observatory, and this captures the very high-energy light beyond the visible range. Now notice the very bright region in all three images. It corresponds to an area of very concentrated energy in each of the respective ranges. Now keep your eye on the spot as we merge the three images. Now, all three images combine to give us a spectacular view of the galaxy's central region. Of course, the high energy spot is the actual center. And here's a larger view of the area. As mentioned, this is the galactic center. The region is called Sagittarius A. Within Sagittarius A, there's another small but very strong source of radiation called Sagittarius A star. and Sagittarius A star is our very own supermassive black hole. Hubble has found that most galaxies have supermassive black holes in their centers. Now, black holes are wondrously mysterious objects, but they are the subject of another lecture. Now let's move on to the life cycle of stars. Stars don't live forever. I've already mentioned that some stars live longer than others. So what is the lifespan of stars? Well, stars can live anywhere from a few million to several billion years. Now, obviously, we cannot study the life of a single star from its beginning to its end, but what we can do is study many stars at various stages of their lives to put together an overall picture of the evolutionary process of stars. As we will see, all stars are born in giant clouds of interstellar gas and dust. They spend about 90% of their life in a very stable phase called the main sequence. Our sun is about 5 billion years old, and it's in the middle of this phase. Once stars have used up their internal fuel, they begin to die. The way they die depends on their initial or their birth mass. Some stars will die quietly as a planetary nebula and eventually a white dwarf. And this will be the fate of our sun in about 5 billion years. And some will die violently as a supernova explosion, leaving behind mysterious things such as neutron stars and black holes. So let's take a look at how Hubble has captured the birth and death stages of stars. We start with this beautiful star-forming region, the Orion Nebula. Some of Hubble's most breathtaking images are of star-forming regions. The Orion Nebula is the closest star-forming region to Earth. This is where stars are born. These regions are giant clouds of interstellar gas and dust and are called nebulae, from the Latin word for cloud. Portions of these areas of interstellar gas and dust become gravitationally unstable and collapse to form new stars. During the gravitational collapse, heat and pressure build up in the core until nuclear fusion of hydrogen into helium occurs, and that is when a star is born. The dark areas within the nebula indicate very dense areas of gas and dust. And the beautiful colors that we see are from ionized gases from the newly formed stars. Also in Orion is the famous Horsehead Nebula. This image is captured in the near infrared. And the Horsehead Nebula is a formation known as a pillar of gas and dust. This is a close-up as seen both in the visible and infrared spectrum. Since much of the visible light is blocked by the gas and dust, the nebula appears like a dark cloud. But infrared light can pass through the gas and dust and allows us to see much more detail. Another animal-like formation is found in the Trifid Nebula, and this sort of looks like a snail's head. The eye stalks of the snail are very interesting. One of them is a pillar of gas and dust, while the other is one half of a bipolar jet from a protostar. A protostar is a star in its last stages of formation before it is fully born. As material collapses towards the center of the newly forming star, some of the material gets ejected out along the axis of rotation, forming jets in opposite directions. This is a beautiful ground-based image of the Eagle Nebula, and Hubble has zoomed in on two of these areas in particular. The first one is this long stellar spire, and the second one is one of Hubble's most famous images. As we look at these two areas, keep in mind their size relative to the overall size of the nebula. Here is the first one. It appears like a winged fairy tale-like creature standing on a pedestal. And the second image is the famously named Pillars of Creation. And they're named such because stars are forming inside of these giant pillars. The tips of the columns are illuminated by ultraviolet light from hot, massive newborn stars. Now, when I say giant, it doesn't quite give a real sense of how big these are. The tallest column in the pillars image is 4 light years tall. That's 24 trillion miles. And the cute little fairy tale-like creature in the first image is 9.5 light years high. That's 57 trillion miles, more than twice the distance to our sun's nearest star. And remember how small these areas appeared relative to the overall Eagle Nebula. Here is the 25th anniversary release of Pillars. And they also released it in the infrared, showing a tremendous amount of stars not seen in the visible image. But quite possibly the infrared image is not quite as beautiful as the visible. This is a magnificent panoramic view of the central region of the Carina Nebula. Hubble has zoomed in on many of the areas in the Carina Nebula, but this is a particularly beautiful one. It is very appropriately called Mystic Mountain. And at the tip of the mountain, we see bipolar jets, which are signposts for the birth of a new star. This image is simply breathtaking. The Lagoon Nebula is a vast stellar nursery with a massive young star at its center. The star is 200,000 times brighter than our sun. The stellar winds from this massive young star are carving out and sculpting a fantasy-like landscape of cavities, ridges, and mountains of gas and dust. This is an infrared image of the Monkey Head Nebula, where the newly formed stars are blasting away dust within the nebula, forming these beautiful giant pillars of gas. The Hubble Nebula is an enormous bubble of hot gas being blown out into space by a super hot, massive young star. The outer edge of the bubble is formed by the hot gas interacting with the cold interstellar gas in front of it. And with this image, Hubble gives us a front row seat to the beautiful interaction of this young star with its environment. We end the part on stellar formation with Hubble's 30th anniversary portrait. It is a vast star-forming region in the Large Magellanic Cloud. It is nicknamed Cosmic Reef because the giant red nebula and its smaller blue neighbor resemble a beautiful undersea world. The sublime image gives us an insight on how young, energetic stars illuminate and sculpt their birthplaces. Before we move on to the death of stars, let's take a look at 3 particularly beautiful and interesting stars. The first is Ares Puppis, the brightest Cepheid variable star. A Cepheid variable is a star whose brightness varies with a fixed period. Ares Puppis is shrouded by a thick, dark cloud, enabling a phenomenon known as a light echo. So a light echo is produced when light from a rapidly brightening object is reflected off of interstellar dust. Another beautiful example of a light echo surrounding a star is V838 Monocerotis. This is a beautiful sequence of an expanding halo of light. In 2002, Hubble observed a significant outburst of light and has been monitoring its evolution ever since. The star is of great interest because an outburst like this had never been seen before. The illumination of the interstellar dust comes from the red supergiant in the middle of these images. And here we see it in 2005 and 2006 as it continues to propagate outward. This is a beautiful detail of the binary star system Eta Carinae, with the larger of the two stars nearing the end of its life. These images were taken a few years apart and with different cameras. The outburst that produced the outflow of material that we see here was initially observed in 1843, but of course telescopes were not powerful enough then to see the details. Eta Carinae is one of the closest stars to Earth that is likely to explode in a massive supernova in the relatively near future. And with this, we segue into our next topic, the final stages of a star's life. The death of a star depends on its initial, or also known as its birth mass. Stars that are up to 8 times the mass of our Sun will end quietly as a beautiful planetary nebula and ultimately as a white dwarf, while stars that are greater than 10 solar masses will explode violently as a supernova, leaving behind either a neutron star or a black hole. We start with this beautiful planetary nebula called the Helix Nebula. Now, despite their misleading historical name, a planetary nebula is a bubble of expanding and glowing ionized gas surrounding a dying star. In about 5 billion years, our Sun will evolve into a planetary nebula and eventually a white dwarf. Now, in the interest of time, I can't talk in detail about stellar evolution, but very briefly, a star's life is a continual struggle between a gravitational collapse and the outward radiation pressure fueled by nuclear fusion in their cores. But stars eventually run out of fuel. And when that happens, the star continues to collapse and eventually reignites new nuclear fusion reactions. When this happens, the star becomes a red giant and expands greatly in size. Eventually, all of the rest of the fuel is used up, so there are no more nuclear fusion reactions in the core, and what is left is a very hot and dense white dwarf. The leftover gases that made up the outer part of the red giant now simply slowly drift away, producing the beautiful clouds of glowing ionized gas. Now, as we will see, planetary nebulae are all very different. One of the beauties of these images is that they raise a lot more questions than they provide answers. One way of getting a better understanding of these nebulae is to look at many of them in the hopes of finding similarities and to help understand the death process of a Sun-like star. So let's just enjoy some of these beautiful images. We will see that these planetary nebulae are all very different and have been given nicknames for obvious reasons. But notice that they all have a white dwarf in their centers, their stellar corpse. Here are 2 other beautiful planetary nebula, and once again you can see their stellar corpse, the white dwarf, in their centers. And we will just look at a few of these beautiful nebula and notice that they're all very, very different, but they all have their white dwarf stellar remnant at their centers. Now, these are examples of what are known as bipolar ejection nebulas. Now, for reasons that are not completely understood, these stars eject their outer layers in a bipolar fashion. And this is the beautiful Butterfly Nebula, imaged with 2 different filters. Now, from all of these images, it's pretty clear that the final evolutionary stage of a Sun-like star is much more complicated than just blowing out the outer envelope of gas. So there is still a lot of astrophysics to discover behind these beautiful images. Now, while Sun-like stars quietly shed their outer layers and end up as a white dwarf, the fate of more massive stars is quite different. Stars greater than 10 solar masses will explode in what is called a supernova. And this is a beautiful remnant of such an explosion. Now, very briefly, all stars are basically giant nuclear furnaces, fusing together lighter elements into heavier ones in their cores. Now, when all their fuel is used up in the core, the star collapses. But since it's so massive, it catastrophically collapses and explodes, sending out all the elements it produced in its core during its lifetime into space. This is, by the way, where all of the elements required for life on Earth originally come from. This is called the Crab Nebula. Its progenitor supernova was observed by Chinese observers in 1054. Supernovae are designated by the year in which they were discovered. So this is what it looks like 1,000 years after it exploded, and it is still expanding at a rate of 1 mile per second. Now, this image was taken by Hubble in the visible light range, and it appears a bit hazy in the center of the image. But if we look at it with a composite image from the Spitzer in the infrared, Hubble in the visible, and Chandra in the X-ray, we clearly see an image emerging in the X-ray spectrum. In the center is a rapidly rotating neutron star called a pulsar. This is the remnant of the most recent supernova to have been observed by the naked eye in our own galaxy. It was first observed in 1604. What we see today is how the explosion has evolved over 400 years. This composite image shows a fast-moving shell of iron-rich material surrounded by an expanding shock wave. It is currently expanding at a rate of 1,200 miles per second. This is the most recent supernova observed by the naked eye. It was first observed in 1987 in the Large Magellanic Cloud. The beauty of this supernova is that its evolution can be observed and studied starting very shortly after the explosion. These images were taken between 1994 and 2016. And first we notice a brightening of the ring of gas surrounding the exploded star. We also notice that the central structure inside the ring has grown. This beautiful composite shows how the supernova has evolved over the 30 years since its explosion. Continuing to observe this supernova will provide insight into the last stages of stellar evolution of massive stars. Now, interestingly, we do not see a leftover neutron star in the center, so it is possible that there may be a black hole, but it's still too early to tell. This is the famous supernova remnant Cassiopeia A, as seen by the Hubble Space Telescope. This is the youngest known remnant from a supernova explosion in our own Milky Way galaxy. It is estimated that the light from the progenitor supernova would have reached Earth about 300 years ago, well after the invention of the telescope, yet mysteriously history makes no mention of it. And this is a beautiful composite image of the remnant. The neutron star can be clearly seen in the X-ray image as a sharp dot in the center. Here are two beautiful supernova remnants, although their progenitor supernova were not recorded. Supernova remnants are a snapshot in time of the process through which the death of massive stars seed the interstellar medium with the heavy elements. The shock wave produced by a supernova explosion can also stimulate the formation of new stars and planetary systems. Analysis of supernova and their remnants help us to understand the evolution of the universe. We now begin our journey deeper into space, away from our galactic home and towards other galaxies. A galaxy is a collection of gravitationally bound stars. Today, we are all pretty comfortable with the idea of a vast universe containing billions of star systems, but this idea only became firmly established about 95 years ago. Until the 1920s, astronomers knew galaxies as fuzzy nebular objects. they did not recognize them as individual star systems. In 1925, American astronomer Edwin Hubble discovered that the mysterious nebulae were actually galaxies outside of our own galaxy. And not only did he discover that there are other galaxies out there, he also discovered that they're all moving away from each other, and the more distant ones are moving away at greater velocities. So what he discovered was the universe is expanding. Hubble's discoveries dramatically changed the face of the universe, and he is rightly considered the greatest astronomer of the 20th century. In this presentation, we will simply enjoy some beautiful close-ups of nearby galaxies, then take a brief look at galaxies far, far away. This is a beautiful example of a spiral galaxy. They get their name from the spiraling arms extending from the center. Most star formation occurs in the arms of spiral galaxies. Darker areas within the arms indicate dense areas of gas and dust from which stars are born. Now, this image also shows a smaller interacting galaxies, but we'll come back to those in a few slides. This is what a spiral galaxy looks like when it's viewed head-on. But if it's viewed edge-on, it appears like a flat disk. And this is the magnificent Sombrero Galaxy. It appears as a flat disk with a halo of stars surrounding the galactic center. And of course, it's the spiraling arms form the disk. Another beautiful spiral galaxy is the Pinwheel Galaxy. Young, hot blue stars can be seen in the spiraling arms. This is a barred spiral galaxy. They are called such because the arms extend from a bar-like structure of stars that goes through the center. Our Milky Way is actually a barred spiral galaxy. Another gorgeous spiral galaxy with very obvious bluish clusters of young stars. And also you can notice in this image, you can see some galaxies in the background. This is the beautiful Andromeda Galaxy. It is our closest large galactic neighbor. Now, although Edwin Hubble discovered that on a large scale galaxies are moving away from each other, it turns out that on a smaller scale, galaxies can group together in clusters due to their mutual gravitational attractions. And galaxies within a group or a cluster can actually move toward each other. And so Andromeda and Milky Way galaxies are actually moving toward each other and will collide and merge in about 4 billion years. So not to worry, we still have plenty of time to figure things out. In the next few slides, we'll see images of interacting galaxies. As I just mentioned, galaxies are often clustered together, and sometimes they can interact with each other and eventually merge. So these two galaxies will continue to swirl around each other, exchanging gas, dust, and stars, until in a few billion years, they will become one galaxy. As galaxies interact, gas and dust flows from one to the other, often distorting the galaxies and giving us some spectacular views. Here's a beautiful example of a pair of galaxies that are tidally distorted through the mutual gravitational attraction. This pair of interacting galaxies is called the celestial bird, for obvious reasons. And in it, we see a spiral galaxy being stretched by the interaction of an elliptical galaxy. Our last slide on interacting galaxies is the beautiful image of the Antennae galaxies. These two galaxies have gone beyond just interacting at a distance and are in the merging process. They are currently going through what is called a starburst phase, in which the collision of clouds of gas and dust sparks rapid star formation. And this gives us a peek into what the Milky Way-Andromeda merger may look like. Now we start our journey to galaxies far, far away with this beautiful image. First thing we noticed are some very obvious spiral and elliptical galaxies. Now these bright points of light are simply foreground stars, and although they are very pretty, they are really of no interest in these images. All other points of lights that you can see in this image are faraway galaxies. The foreground galaxies are 450 million light years away. A light year is the distance that light travels in 1 year. So this means that when we look at these galaxies, we are seeing what they were like 450 million years ago. In other words, we are looking into the past. And this is why the deeper we can look into space, the farther back in time we see. This beautiful cluster of galaxies is 2.2 billion light years away. So we are looking at 2.2 billion years into the past. Everything you see here, with the exception of a few obvious foreground stars, is a galaxy. Now, notice the stretching of light around the center of the cluster. We can see that some of the light is stretched along arches, and we will come back to what this means later. This cluster is 2.3 billion light years away. The stretching of light is even more obvious in this image. With this image, we're looking at 4 billion years into the past. And once again, we see the stretching of light. This is a phenomenon known as gravitational lensing, or the bending and stretching of light as it passes through a gravitational field. What this means is that there are galaxies behind this cluster whose light we see as stretched by the cluster's gravitational field. So if this cluster is 4 billion light years away, and there are galaxies behind it whose light we see stretched and bent by the gravitational field, the question is, how far back can we see? This is called the Hubble Deep Field. It is Hubble's initial attempt to push the limit in imaging distant galaxies. Some of the dimmest galaxies in this image are 12 billion light years away. Now, how this image came about is a pretty interesting story. The director of the Space Telescope Science Institute has 10% of Hubble time to allocate at his or her discretion. The other 90% is awarded competitively. In 1995, the director very boldly said, "Let's just point it into space and see what we find." So they pointed Hubble towards a very dark area near the Big Dipper for 10 consecutive days. And what they found was this amazing zoo of galaxies. Many of the distant galaxies in this image are very oddly shaped galaxies, which is consistent with the evolving universe expectations of the Big Bang Theory. Given the wonderful success of the Hubble Deep Field, an even more ambitious effort was launched in 2003 using upgraded cameras and pointing Hubble for 27 consecutive days on a very small and dark area in the southern hemisphere. This image, called the Hubble Ultra Deep Field, was released in 2009. The most distant object is 13 billion light years away, so we are looking at 13 billion years into the past. It contains over 10,000 galaxies over an area of the sky that is equal to the width of a dime, held at 75 feet away. If we take this galaxy density and spread it out over the sky, it yields over 130 billion galaxies in our observable universe. It is absolutely amazing. Less than 100 years ago, we thought that the Milky Way was the entire universe. Just like in the Hubble Deep Field, the more distant galaxies are smaller and oddly shaped compared to the galaxies in our local universe. So this clearly shows that galaxies evolve over time. In 2012, the Hubble Extreme Deep Field was released. This image was assembled by combining 10 years of Hubble photographs taken at the center of the original Hubble Ultra Deep Field. Using Hubble's near-infrared cameras, it reaches much fainter galaxies, enabling the study of some of the earliest galaxies in the universe, going as far back as 13.2 billion years, when the universe was only 600 million years old. And this is Hubble's most comprehensive deep space image. It combines the full range of wavelengths of light available to the Hubble Space Telescope, ranging from the near-infrared to the visible to the ultraviolet, and providing us with the most comprehensive picture of our evolving universe. In 2016, Hubble discovered the farthest galaxy ever seen in the universe, at a distance of 13.4 billion light years. In other words, we see it as it was 13.4 billion years ago, just 400 million years after the Big Bang, about 200 million years after the first stars started to form. But what about before that? Can we push Hubble to look deeper into the very infant universe? Well, unfortunately, the very first stars are probably too faint for Hubble. So this shows us that even Hubble has its limit. So what's next? How do we look even deeper into space to probe the very infant universe? The successor to Hubble is the James Webb Space Telescope. It is projected to launch in 2021. Whereas Hubble is optimized for observations in the visible light range, Webb will be optimized for the infrared so it can peer deeper into space. Webb will operate much farther from Earth at a distance of 1 million miles. Recall that Hubble is less than 400 miles from Earth. One of the science goals of Webb will be to study planetary system formation. Stars and planets form from very massive clouds of gas and dust, as we've seen in some beautiful images, but they block out the visible light. But we can penetrate these clouds by observing the infrared light that passes through. The other main science goal, and what I think is more exciting, is to see the first stars and galaxies that formed in the very early universe. As we can see here, Hubble can only go so far because light from the very early universe is redshifted beyond Hubble's range. Since Webb will be optimized for the infrared, it will be able to look deeper into space and therefore farther back in time to see the infant universe as it emerges from the dark ages. The Hubble Space Telescope has truly revolutionized our knowledge of the universe. Not only have its spectacular images shown us a view of the universe beyond our imagination, but its discoveries have fundamentally changed our understanding of the universe in which we live. I hope you've enjoyed our journey through the universe as seen through Hubble's most iconic images. If you would like to learn more about our amazing universe, please join me in my upcoming 6-part lecture series, Cosmology, the Study of the Universe. If you would like to receive notifications of when these lectures are posted, please subscribe to this channel. Once again, I hope you've enjoyed today's journey through our universe, and thank you for watching.